You're not talking.
Did you hear me?
I can hear you, yeah.
All right.
Hi, everybody, and welcome along to the AMTech Solid State Controls webinar today. We're going to be discussing transformers and how they're used in UPS systems. As always, if you can hear me, please type in the chat bar to let me know that everybody can hear me. And that leads me on to my first point with Webinar Jam, which is the platform that we use for our webinars. There is about a 30-second delay from when I'm speaking to when I see the comments come up in the chat bar. So there is a little bit of a lag. It is designed that way because this webinar goes out to Windows platforms, iOS platforms, and all that kind of stuff. So they do have to do some processing before it gets to you. Thank you, everybody, for letting me know you can hear me. Excellent. The webinar today is going to be presented by Don Imlay. He's our training manager and inverter subject matter expert, and he is a transformer whiz. So he originally started off in the transformer department when he got started in the industry, but I'll let him tell you all about that. In the platform that we use, Webinar Jam, it has a panic button. So basically, if something goes wrong with the presentation or with the webinar and it freezes or does something, I can press the panic button and it will create a new room for everybody, and we will carry on going as if, hopefully, as if nothing happened. I've never had to use it so far, so hopefully that remains the same. The webinar will be recorded. And if you registered for the webinar, you will have access to the recording. You'll be sent a link. And also what our marketing department does is they will also download the video to our YouTube channel, because the recording that you get on Webinar Jam, you can't fast forward or rewind. It's treated like a brand new webinar. But when we put it on the YouTube channel, you can fast forward, rewind, and pause and do whatever you need to do. So it gives you more flexibility. So that's really about it. So what I'm going to do is I'm going to mute myself in just a moment and let Don introduce himself. We also have Mario Jr. on the call. He is one of the engineers in our transformer department. So if there's any questions that Don can't answer or that I can't answer, then Mario will be available to answer those questions as well. What we tend to do is we tend to wait until the very end of the webinar to answer any questions. So if you do have a question, put it in the chat bar and we'll go through those questions at the end. So I think that's about it. Also, please remember, most of us are working from home just now because of the COVID-19. So if you hear dogs barking in the background or something else, please excuse us. We are doing our best in the situation that we're in. So without further ado, I will hand this over to Don.
Well, good morning, everyone. Hopefully you can hear me okay. As Craig said, my name is Don Imlay, and I'm the training manager here at Solid State Controls. I've presented about, I don't know, somewhere more than 300 UPS seminars over the last 20 years or so. But this is my first webinar, so it's kind of a new thing for me here. I've been at SCI more than 35 years now. In that time, I've worked as a field engineer, test technician, which is where I started out. I did some circuit design on some circuit boards. I've played service manager, technical writer, a few other things. When I got this job, I'd never heard of a UPS. And I went in the interview wondering why the guys with brown trucks wanted to hire an electrician or a technician or something. But I just wanted a job. So I got into the interview and found out, hey, this was not about brown trucks, but about some kind of power supply. So I got the job and went on from there. Prior to taking on this position or working at SCI, I started out at a transformer shop when I got out of school. And I learned more about transformers than I ever wanted to know, and didn't really care for it because it wasn't very exciting. And so I left there and got on at the R&D department in Westinghouse, where we built aircraft inverters. And that was a lot of fun. From there, I went to the opposite end of the spectrum, working underground for an underground mining equipment manufacturer. That's a whole new world, life underground there. And from there, went on to professional sound and light engineering company or contractor, and did all kinds of rock and roll bands and that sort of thing. So that's a little background on where I've been and so on. As Craig already said, questions and so on, we'll address at the end and as time allows. A few things we want to accomplish here: understand the functions of transformers in UPS systems with the advantages and disadvantages of them. We're going to talk about transformer basic configurations and types, voltage, current, and regulating transformers. And we'll finish up with a little discussion on how we build transformers at SCI, some of the processes and so on. Most of the transformers, excuse me, my screen's not looking good for me right now. Anyhow, this is just a picture of the transformers there at the shop in the factory. The thing that's good about building your own transformers, we've got total control over the whole process. And if something comes up, if there's an emergency, maybe something fails in the field, we can stop the production if we need to and go right to building a new transformer to get something out to the client. So that's something that's really good about having control over your transformer shop. We don't have to go out to a vendor and get in line with anybody else. Transformer is a device that transfers electrical energy from one circuit to another through inductively coupled conductors. Transformers work with some form of AC. The waveform could be a sine wave, square wave, or in some inverters, it's a series of pulses. Here we're showing a transformer, basic coil and so on. The magnetic field in a coil wire is called the primary. It induces a magnetic flux in the transformer coil, in the iron core. The secondary, which is usually wound on the same coil as the primary, has the magnetic flux induced into it. The secondary voltage is a ratio between the number of turns on the primary and the number of turns on the secondary, and this is called turns ratio. From a practical standpoint, the transformer is more than about 95% efficient. So a transformer where the secondary voltage is lower than the primary voltage is called a step-down transformer. Secondary wire size, consequently, is larger than the wire size of the primary. Later on, we'll see why that can be important for us. An isolation transformer provides flexibility in achieving desired voltage while providing galvanic isolation to the secondary. The image at the bottom is the end view of the coil. Dots on the transformer schematic indicate polarity, as you can see on the schematic at the top. At the bottom on the coil there, the red lead is the start of the primary and the blue lead is the finish. The black lead is the start of the secondary and the yellow lead is the finish. Again, being able to identify these leads can help us when we if we have to hook up the transformer in the field. Here's a typical transformer, 120 volt primary, two 12 volt secondaries. If we put these in series by tying the finish of the top coil to the start, again, which is noted by the dot of the bottom coil, we get 24 volts on the output at 1 amp. If we parallel the two secondaries, we'll get 12 volts at 2 amps. Here is a common transformer used in industry, often used in bypass sources on single-phase UPSs. It's got two primaries, or two primary windings, and two secondaries. In this configuration, the output, which is probably the most common we see, is 120 volts and 480 on the input. Here's the same transformer reconfigured, still with the 480 volt primary, but 240 on the secondary. This is a common, at least the secondary configuration is common for residential use here in the US, where we call it a split phase. So it's 120 volt phase to neutral and then 240 volts phase to phase. I hear people talk about 110 volts all the time. I don't know that that exists in this country, but a lot of people like to call it 110 volts. The standard's 120 volts. Here's another transformer, the same transformer, but configured for 240 on the input, 120 volts on the output. And last, a 240 to 240 configuration. Maybe the neutral is used here. Maybe they don't need 120 volts, but only need isolation, which is what this serves. Auto transformers. An auto transformer gets its name from the word auto, or Greek for self, and refers to a single coil acting on itself and not to any kind of actual auto mechanism or anything like that. In an auto transformer, portions of the same winding act as both the primary and secondary. The advantage for auto transformers is they're smaller, lighter, and cheaper than dual winding transformers. However, they provide no isolation. Here's a typical application for an auto transformer. The finish of the primary, the 208 volt input at the bottom here, is connected to the start of the secondary, the 32 volt winding, and then the output is 240 volts. It should be noted that the primary does not have to produce full power at 208 volts. It only has to produce full power at 32 volts. Consequently, the iron core in the auto transformer is going to be much smaller, which is why it's physically smaller. Again, auto transformers provide no isolation. Current transformers. A current transformer measures current typically and just steps it down. The secondary of a current transformer typically either drives a meter or converts the primary current, drives a meter, or it's sent to a sensing circuit. Typical for our UPSs, we'll have current transformers on the output of the system, and we often use them on the input to a battery charger to measure input current. With a current transformer, the leads have to be terminated at all time because we're pumping current through the primary. There has to be secondary current also. So if you have to change out, say, a meter that's driven by a current transformer, while the meter is being changed out, the leads on the secondary would need to be tied together. CTs are, the primary is actually, the load cable. And the cable inserted into the donut and then connected to the load. The load cable then has a one-turn primary. Number of turns on the secondary determines the ratio. Therefore, if the CT has 100 turns, the ratio is 100 to 1. When there are 100 amps of current, there would be 1 amp of secondary current. If you're a manufacturer, such as SCI, you want to minimize the number of parts in inventory you have and the number of part numbers then. So you can take a 400 to 5 CT, and if you put 2 turns through the primary, it becomes a 200 to 5 CT. And you could use the same CT with 4 turns on it and end up with a 100 to 5 CT. So one current transformer, one part number, can serve multiple applications then. And here's just a picture of a typical CT showing the donut right here with the 1 turn through the primary. And again, this one's driving an amp meter. Power transformers can be physically large and quite expensive. Commercial UPS systems found in office buildings and data centers often eliminate these transformers. There are advantages to this. You gain some slight efficiency. Certainly, if you get rid of transformers, your cost goes down and the footprint of your machine goes down. All those are important, especially in commercial buildings. But there's disadvantages to that also. Primarily, the loss of isolation, input to output. In industry, it's not an ideal controlled environment, or rarely is. Transformerless UPSs substitute complex circuitry, such as in the battery charger, at higher voltages, and the reliability is just not there, not compared to the traditional UPS. Lack of galvanic isolation exposes maintenance personnel to greater risks. Typical ground fault sensing is required to shut down the transformerless UPS to make sure it cannot backfeed the bus, or if there's a ground fault in the 480 distribution. From here, we're going to look at a brief overview of a UPS, and I'm going to talk about just the very basics of it first, and then we're going to look at these areas where we put transformers and why we do it. First, we've got a rectifier. Typically, that's 480 volts. There are a few applications that run 208, but they're pretty rare and they're lower power. And a few of our clients run a 600 volt bus, but typically it's 480. That goes into a rectifier and converts that voltage to DC. Coming out, we've got DC that's also feeding the battery and goes into the inverter. The inverter switches the DC off and on the output we've got AC. This can be single phase, three phase, just about any voltage you want. We also have a bypass source, typically, and coming into the static transfer switch on the UPS. Preferably, we've got a isolation transformer right there for the bypass source, which would be considered separately derived. So, looking at our input power, a loss of AC input, and again, the battery provides the DC to run the inverter, and so on. Here's the distribution we see typical for a plant environment. We've got a 480 bus with a high resistance grounding scheme. Okay. The advantage of the high resistance ground is that ground faults in a ground, if there is a ground fault, it limits fault current, and the critical equipment out there running off this MCC can continue to operate without tripping breakers. Now, of course, if we have a fault on two phases, then we're going to trip breakers, but one fault does not trip a breaker. Here is the typical 6-pulse rectifier that the vast majority of our UPS systems use. 480 volt input feeds a delta transformer. The input transformer, of course, provides galvanic isolation from the secondary. And the secondary then is configured for whatever voltage we need. Typically, on a 125 volt DC system, the phase-to-phase voltage will be around the neighborhood of 130 volts. One important thing, again, is ground faults upstream do not affect the operation of this battery charger. Eliminating this transformer here poses safety risks to maintenance personnel. And that's quite common in the commercial, again, the commercial UPSs. Your battery now back through the rectifier is referenced to ground and provides more safety concerns, again, for maintenance people. The 6-pulse charger here with the secondary is not grounded, which allows the DC voltage to float. So if we have distribution maybe multiple breakers coming off this battery charger, a ground fault out in the DC load, again, if say positive goes to ground, does not trip breakers, it does give an alarm. I really like this kind of battery charger because it's simple. SCRs are the rectifier. They are incredibly reliable and rarely ever fail. This battery charger, therefore, is very simple. The controls are simple, and they just run and run and run and run. Sometimes we see an application where the client wants to minimize input current distortion, and they're really concerned about the power factor presented by the rectifier. When that happens, we build what we call a 12-pulse rectifier, and that uses on the secondary of the transformer a delta secondary and a Y secondary. Each feeds its own rectifier bridge. The phase shift between the delta and the Y results in a rectified voltage that, when you sum it together, improves the power factor. So here is, I'm showing the red, the Y bridge as a rectified voltage, and the blue is the delta bridge. And at the bottom, they are summed together. What's important is what we see next. This is the input current waveform. So this is a 12-pulse rectifier, a 6-pulse. In one 60 hertz cycle, we're going to count 12 current pulses here. Okay, now, if you look at the peak, you'll notice, and in this case, even the looking at the negative half cycle, those peak currents, they don't last very long, but it's a pretty big spike in current. Now, this is a normal current waveform, but the distribution system has to be able to supply these current pulses. Okay. The next one we're going to see is the 12-pulse waveform. And if you look carefully, you can count 12 pulses there. The last pulse right before the zero crossings doesn't show up so well. But there are 12 pulses there, and you can see the current spikes are smaller. And the waveform approximates a sine wave. All right, on to the inverter. All of the SCI inverters include some kind of a output transformer. The inverter transformer provides galvanic isolation, of course, and allows us to tune the voltage for what we need. And when coupled with the bypass transformer, the output, the UPS output then has neutral bonded to ground locally. SCI builds both ferroresonant and pulse width modulated inverters. Ferroresonance is a passive type regulating transformer, and it accomplishes this with inductors and capacitors. Pulse width modulation is an active circuit employing feedback to regulate output voltage. I'm not going to go into details on this. Craig discussed this in a previous seminar. I just wanted to mention it right here. Pulse width modulation switches DC off and on at a rate of 10 kilohertz. The ratio of on time to off time changes for each pulse to give the proper output voltage. and the string of pulses then is filtered to provide a sine wave. The one nice thing about this is that the microprocessors we've got today allow us to look at output waveforms and sample them really fast, and the output of the system is very fast to respond to changes in load and output and input voltage. The ferroresonance systems, on the other hand, operate at 60 hertz, and we just built a 60 hertz square wave driving the input to the transformer. The transformer, the ferro transformer secondary, operates in a form of magnetic saturation. The saturation voltage, and consequently the output voltage, is determined by the capacitor. Severe overloads on a ferro cause it to fall out of resonance, and it then limits the output current and doesn't trip breakers. A ferro will run into a dead short, and for dramatic purposes, I demonstrate this when I do a training class. Another advantage of the ferro is stored magnetic energy provides for superior fault clearing. Ferros will clear faults in a distribution system. If we have a proper distribution panel, preferably with high-speed fuses and switches, ferros will do a great job of clearing faults out there. Our bypass transformer is next. Why would we want a bypass transformer? The transformer provides isolation. That's the main advantage. Also, it doesn't share, again, it's separately derived, and it doesn't share load current with any other equipment out in the plant. So we don't have issues or the potential issues for noise and things like that. And again, fault clearing is improved. In commercial applications, they sometimes tie off the bypass input right off the AC input to the battery charger. And there's an advantage to that. It's a cost-cutting scheme. The downside is that if you have an extended power failure, you've lost the AC input, of course, to the battery charger, but also you've lost the bypass source. So once we run out of batteries, then you're going to lose the load. So in a preferred installation, the bypass source is fed from preferably a separate MCC than the battery charger. So the goal is hopefully we never lose both sources at once. If we lose the bypass, we're still got the rectifier running. If we lose the AC input, we run on batteries. If we can't get it AC input restored, then we still got the bypass to go to. Okay. One other thing about bypass transformers, they should be larger than the kVA rating of the UPS. So let's say we have maybe a 30 kVA UPS, we'd probably go with a 50 kVA bypass transformer. And the reasoning behind that is we want to make sure we've got capability if there is a sustained overload. We overload the UPS, we want the bypass source to still be able to provide that overload until we can get it straightened out. System output transformers. If we have a long distance between the output of the UPS and the load panel, the common specification then would be to provide a 480 volt three-phase UPS and then a step-down transformer at the load. This reduces line losses and again allows for local neutral bonding at the panel. Here is a typical bypass dry type transformer showing different taps that we can select to get the proper output voltage, assuming our AC input voltage to the transformer is not ideal. Maybe that's only running at 460 volts. Well, we've got a tap we can select there to get the proper output voltage. Typically, when we set up our UPSs, and I'll refer to a single phase system here, we're going to set the output of the system up. If it's specified at 120 volts, we'll set it up so we run a little bit on the high side, somewhere around 121, 122, maybe 123. And the goal then is to have that take into consideration the line losses between the UPS and the actual load, so that at the panel board we're feeding, even if we've got some cable drops, we still have a good 120 volts there. Here's a three-phase transformer, 480 to typically 12208. And again, we've got taps on there to select the proper voltage. Oftentimes these transformers go in and nobody bothers to look at the taps it's set on, and maybe they're set up because the 480 bus doesn't run 480 volts. Maybe it's only, again, 460, 465, something like that. So the output voltage is already low coming out of the bypass transformer. Maybe it's down to 116 volts, something like that. If we have overloads on a system, the UPS, if it's overloaded, will transfer to the bypass. That's the function of the static switch. And what we don't want to see then is a low bypass voltage with no load. And when you put load on it, then the voltage drops further. And by the time we get out to the loads, we could be down in the low teens, maybe 111 volts. And we're approaching the minimum input voltage of the load then. So to combat that, we've got a number of different types of transformers or different technologies to regulate the bypass voltage. The four common ones are ferroresonant, something called a tap changer, a magnetic amplifier known as a mag amp, and a variac that's motor driven. Whether it's driven by an inverter with a square wave or a sine wave, the ferroresonant transformer doesn't really care too much what the input voltage waveform is, but it's got filters on the output and will provide a clean regulated output voltage. So really the ferro doesn't care what you put into it for the most part. It cleans it up. RMS voltage is what's important. When we use a ferroresonant regulating transformer for a bypass source, we refer to those as isolimiters. Tap changers are typically an isolation transformer, and the secondary has multiple taps on them. Monitoring circuitry will then adjust the taps, turn on a set of SCRs as we show here, to select the proper output voltage. Again, SCRs are used versus mechanical contacts for reliability and to prevent arcing. Typical, although I don't show it, is they'll fuse each tap here. Many years ago, I first experienced tap changers. About 30 years ago was my introduction to them, because we'd put a tap changer in a UPS, and I got the phone call when this thing failed. And I got a sour taste in my mouth for tap changers at that time. So when SCI brought out a tap changer a couple years ago, initially I was not too impressed with it, because all I'd had was bad experience. Then I saw the design and I thought, man, this is really a nice design. They eliminated all the problems that I'd experienced before. So I think the tap changer we build now is a really nice, reliable design, and I like it. And I thought I'd never say that about a tap changer. So the advantages of tap changers: they regulate really good, and they're tolerant of wide frequency changes. There is a potential hunting, trying to always find the right output voltage if your feeder is very unstable, and if you see wide changes in input voltages. As I've hinted at, the older designs were prone to SCR failures, and consequently, when the SCRs failed, they took out transformers. I think we've designed that problem out of our new tap changer here, which is why I like it. Mag amps. Our Navy used a lot of mag amps. They first came out in the 1900s, and they were used generally for to provide voltage control for rotating equipment. At that time, there wasn't a very good means of doing this. So the magnetic amplifier allowed for means of controlling voltage. There were audio amplifiers. Now, this is going back into the 1940s and so on, that used magnetic amps and turbine controls and a lot of other equipment before solid-state devices came out. When solid-state devices came out with power devices, that kind of reduced the need for the mag amps. If anybody's a hi-fi nut, you may know that back in the 1980s, there was a company called Carver Corporation that sold home stereo amplifiers. They called a mag amp. It was a mag amp in name only. It did not actually operate like a true magnetic amplifier. The advantages of mag amps are excellent regulating capability over a wide range of input voltage. Reliability, because they're just simple. There's not much to go wrong with them. And you can adjust the output voltage with the potentiometer. Disadvantages, probably the biggest, is that a mag amp, the nominal input and output voltage must be the same. If you want a separate, if you want to say a typical 480 volt input and 120 volts output, you have to have an isolation transformer to go into, excuse me, my phone went off. With the I was supposed to turn my phone off first, and I missed that on the checklist. Anyhow, disadvantage again with the hopefully I put that to bed. Disadvantages with the mag amps again was the separate isolation transformer required for output voltage. If you've got three-phase, you need 3 transformers. Here's a mag amp that we built at the factory. It's a 3-phase mag amp, so there's 3 separate transformers there, and then the bottom front of the cabinet are harmonic filters. A mag amp consists of a primary winding, a series aiding winding, a series opposing winding, a bias winding, and a phase angle controller to produce a DC voltage. This phase angle controller, which is just a glorified battery charger, or circuitry is, monitors output voltage and then produces a corresponding DC voltage. So how this thing works, the voltage in the primary winding induces a voltage on the series aiding winding. The output voltage then with this of the aiding winding is greater than the overall input voltage. The voltage on the opposing winding that is induced from the primary is in series with the aiding winding and is controlled, the voltage on the opposing winding is controlled by a DC voltage on the bias winding. So what we've got is essentially 2 secondaries. One increases the voltage, and then the next one, the opposing winding, decreases the voltage, and it decreases the voltage depending upon a DC bias put on that opposing winding. So in essence, if the input voltage drops, the power supply increases its voltage, which effectively lowers the voltage on the opposing winding, and the output returns to regulation or regulation band. The last transformer used in bypass circuits, regulating transformer, is a motor operated variac. There's typically a meter relay on the output of the transformer. Contacts from the meter relay, if we go out of range, either high or low, suitable contacts close to drive a DC motor. The motor then moves the variac up and down to get back within our voltage, our regulation. The advantage of this transformer, I can't come up with anything. It's a mechanical design. The brushes are a maintenance item. This thing has horrible transient response to changes in output voltage. It's mechanical. The voltage has to sag, and then a motor has to correct for it. They're higher impedance, and they don't have good fault clearing capability. Some people like them. I'm not sure why. I would never want one in my system. So next we're going to look at our manufacturing process. And I've kind of stated this before, but I think it's worth knowing or going across again. Building these transformers in-house provides a lot of flexibility, so we can do what we need to make production schedules. But our most important thing is is the field. If we need to make a transformer to replace one in the field, we don't have to get in line with anybody else. We set the production schedule. So we can turn around the transformer. We can stop everything we need to if we have to build a transformer in an emergency. So when we build a transformer, we start with a specification. There are several pages in the spec. The specification will call out the coil, wire size and type, insulation between the core and windings, core geometry, meaning the size and the type of the steel used in the core. Transformer cores have a variety of different types of steel you use depending on what you need. Thinner, thicker, different types of steel for the application. Once a transformer is built, then it gets impregnated with a resin. The specification calls out the impregnation. It calls out how the terminations are done, whether they have lugs on them or not. And finally, the testing. Here's a picture of a couple pictures here. The one on the left is the transformer shop I worked at almost 40 years ago. Now this transformer, I looked the company up, they're still in business. And this is a current picture here. I called them up and they sent me this picture. This is a small winding machine. It'll do 15 coils simultaneously. And there's a tray right there of a bunch of coils that have been wound. And I'm guessing they're a couple hundred VA, something like that. Thanks, Craig, for that little arrow there. That's the transformer coils there. To the right is a winding machine at our factory. It's a motor drive that's geared way down that will spin less than 100 RPMs or so. And coming out the end of the drive is an arbor with a form on it. And we just set this thing to spinning to build the coil. And you can see this is suspended on the left side of the picture. The arbor is suspended just because it's so heavy right there. So we start with a form insulate with Nomex paper insulation, and then we'll wrap the form with magnet wire. Magnet wire has insulation, not typical like we see in typical cabling, but the insulation is a varnish, which is very thin and makes more efficient use of the space. Smaller transformers use round wire. Most transformers larger than a few kilowatts are wound with rectangular wire. The largest transformers are wound with sheet copper, which is what we just saw. When you use sheet copper, each layer has to be insulated, and we use Nomex paper, which is very high temperature between each layer. So on the left, we've got a choke or inductor with rectangular wire. And then again on the right is our picture of a coil with sheet copper. Here is some coils that will be made up that are already built and will eventually be built as part of a ferroresonant transformer. So on the far left, there's the primary and there's a secondary. And then the third coil will be what we call a harmonic neutralizing coil. And it's what gives us our 2% total harmonic distortion spec. Here's the cores, or different core type material often used right here. On the left, we've got what we call an EI core. And this is typical of smaller transformers, maybe up to a few kVA. In the middle is what we call a C core, and it's been cut in half, and the coil then fits over that. Now, when this is used as an inductor, there will be an insulating material between the gaps on this C core here, and to avoid saturating this core. On the right is strip steel that is cut on a machine at our factory. Here is the strip steel on a roll. That's how we receive it. Now, this roll is almost empty at this point. The roll is considerably larger than that when it first comes in, so there's been a lot of steel taken off of this one right here. It goes to the winding machine shown right here, cutting machine. And this cutting machine uses a guillotine type action across the end to cut the steel to the proper length. Now, the width is predefined, but it cuts the steel to the proper length. Typically, when you shear off sheet metal on like a brake, it leaves a little lip on the end of the steel. This cutting machine here slices the steel perfectly square on the end. It has no lip. If it did have a lip on it, it presents air gaps, and the air gaps, because the steel can't fit together properly, results in heating. So the core runs hot, the transformer runs hotter. Here is the cutting machine here, the end of it, and I think we may have a video for this. So that just shows the machine cutting the steel right there. And I'd like to play that 3 or 4 times in a row if I could, just because you get to hear the machine doing its thing there. It kind of gets you in a sequence. Like, it's kind of fun to listen to. So here again is the cut steel on the end, or on the picture in the right, all stacked up. Here's the core with the steel assembled. The core now, of course, there's no coils on this yet. We do this by hand. The assemblers stack this up, get it ready, and then they'll set the coils down on it. And here is a finished ferroresonant transformer. Okay. You might notice in the right-hand corner, there's a dead blow mallet right there. You don't swing away like you're hitting a ball bat or something with this mallet, but what the mallet does is allow us to tap the steel together and get everything perfectly lined up. So again, we don't have any air gaps around the steel where the pieces come together. Once that's assembled, then you can see the bolts around the edge. All thread rod is used to tighten everything down. Next thing we do is test the machine, the transformer, in what we call green state. Testing includes a high pot which is just high voltage to make sure the insulation is proper. And we'll check turns ratio. Depending on the type of transformer it is, whether it's an inductor, a ferro transformer, or a battery charger transformer, we may check waveform distortion, excitation current, meaning how much current it takes just to make the transformer operate, inductance, and there's another variety of other parameters that we may end up testing depending on the requirements of the transformer. We make any adjustments that we need to meet the spec, and then the transformer goes for impregnation. There's cheap ways to do impregnation. We don't go the cheap route. It's quite laborious. There's a lot of work that goes into this process. It's called the VPI, vacuum pressure impregnation process. We spend a lot of effort with it because these transformers, when they come out, they're going to go into a UPS that's going to do battle for a long time, sometimes 40 years. So we want these things to last. Another advantage to the impregnation process is it actually reduces operating temperature, and the audible noise is considerably reduced. So we take the transformer once it's tested and put it in a tank, which you see here. And this tank goes down in the floor about 10 feet or so. It's pretty deep. We drop it down there, drop the transformer at the bottom of the tank, and then pull the lid closed. And if there's any nuclear people here, this almost looks like a containment building right here. But we lock the lid down and pull a vacuum inside the tank, and that eliminates air and any moisture. Then the chamber is flooded with the resin and totally immerses the transformer. The transformer will sit then in the resin while it penetrates deep inside the coil and the core. After it's penetrated, we've had enough time there, the resin is then pumped out of the tank and the transformer is moved to an oven. Here's the oven where the transformer is cured at. Once we take it out of the oven, then it goes to a department that dresses the leads and lugs the leads as needed. If we have bus bars rather than leads like this coming out, they have a little belt sander they use to sand the resin off of the leads to make connections. Transformers with rectangular wire have a special lug known as a dragon's tooth. The teeth are actually inside the lug, and they do look like a dragon's tooth. When crimped, the teeth penetrate the varnish on the magnet wire to make a connection. The pressure from the crimp actually fuses the wire to the lug. We go one step further in this process and we remove any resin and the insulation off magnet wire prior to putting the lug on. It's just another quality control process to assure we have a good connection there. This shows a transformer here. I use this one because the primary or one of the windings, you can see, has rectangular wire, and the secondary or one of the other windings has sheet copper, and here are the bus bars. coming out. So on many transformers, if we know the input and output voltage, and maybe we don't have really good documentation on how to connect up the transformer, if we know what the voltage should be, we can guess which windings are the primary and the secondary. So let's say this transformer right here has a 480 volt primary and a 120 volt secondary. Can you tell which one is the primary and which is the secondary? The bus bar, is it the primary or is it the secondary? Well, the primary is the rectangular wire. Remember, power in a transformer roughly equals power out. So if we've got 480 volts on the primary, the wire is going to be smaller there, and the secondary has the larger wire size. That's the bus bar there. So even without documentation, we know the secondary here is the one with bus bar. And looking at the bus bar again, we know that the start, which is on the left, is next to the coil. So the finish is the one farther out in the coil. Okay. And that's the end of my presentation. Questions?
Cool. Thank you very much, Don. There are questions. So the first question that came on very, very early was, can we use a step-down transformer as a step-up transformer by using the secondary as the primary?
That's a great question. Of course you can. Wait a minute, Craig, let me make sure I understand that question again.
Okay. Yeah, just use it backwards.
Yeah, run it backwards. Sure,
Yes.
In just an isolation transformer, you can run them backwards. So yeah, you could step up the voltage if you needed to.
Is there any downsides to that, or any issues they might come across, or they can just, as long as they stay within the power rating of the transformer, they're okay? Yeah.
Yeah, sure. That'd be the only concern: is do we have is the transformer capable of producing the output current it needs to?
Cool. And then we have a question asking, is the ferroresonant UPS more reliable than the PWM UPS?
I guess my response would be the ferros have been around for a long, long time. They're very simple circuits. So there's less parts on them, and just by having fewer parts count, you're going to have good reliability. And I'm going to offer my own view on this, but when we introduced a PWM machine or our DPP, again, me, the naysayer, said, why do we have to do this? We got a great machine. They just run and run and run and run. And once I got to looking at the machine, it's really the PWM machines are great machines, and they are reliable, and the inverter bridge is good. And so I don't know that you can say there's one from a reliability standpoint is better than the other one. There's advantages and disadvantages, which is beyond the scope of what we're going to talk about here. But I think they're both good machines.
Okay. Well, and that there was another question asked after that, and it was, are there reasons to pick a PWM inverter over a ferroresonant inverter? But you think we don't have enough time to go over that today?
I can make a summary real quick.
Okay, cool.
The PWM machine is physically smaller. The magnetics are smaller. So the pulse width modulated machine, its advantage is it has a smaller footprint. It's slightly more efficient. So if efficiency is really a concern, that's the advantage I have. Ferroresonance systems are not small, and by the mere operation of the ferro transformer, it's not as efficient. So that's probably the biggest difference.
Okay. Somebody has asked, any comment on the peeling of transformer insulation if the track temperature is within specifications? From your friend Damjan.
Damjan, I'm not sure. I've not seen, I don't think, peeling insulation. I don't think I can offer a good answer there.
Okay, what we'll get is, Damian, if you want to get with Don afterwards, if you want to send a picture of that peeling transformer installation, then that would be good. We can have a look at it and see, we would be able to comment further on what was going on. Somebody else has asked, what would be a good replacement for an old three-phase 480 volt PWM inverter that has no load most of the time? Stay with PWM or switch to ferroresonant?
I'd probably go with the PWM. In this case, I think it depends on what the plant has already. If they've got one of our older ferro machines and the operators know the machine and the electricians know the machine and like it, I would say that would be the guiding, what would guide me for replacement.
Yeah, what I would say to that is for a system that is a 480 volt three-phase output system, we would probably recommend that you would go with another PWM system. We don't tend to make a huge amount of 480 volt three-phase ferroresonance systems anymore. Would I be correct in saying that, Don?
Yeah, that's not that common.
Yeah. But Don has a good point. Go with what you are comfortable with. There's no reason, except for size and footprint, to go with a ferroresonant or a PWM. So we would need more information on the spec for that system, but there's, in truth, there's no good answer for why you would go with a PWM or a ferroresonant on that system, in my opinion. Damian has said they have sent a transformer to us to have a look at it. So I'm interested to see what that is. So we will dive into that and get back to you, Damian. Somebody else asked, let me see down here. I don't know if we've got time for this, but can you elaborate more on the function importance of the output isolation transformer in UPS applications?
The output isolation transformer?
Yes.
Well, again, there's the obvious isolation from input to output, and what's nice about what we call a double conversion UPS system, we run the input AC through a transformer, convert it to DC, and then convert it back to AC. So you've got excellent isolation. Transient voltages and surges don't get through. So we got excellent isolation, and then having with the output transformer, you create a new neutral wire in a grounding scheme that doesn't share any cabling with the rest of the plant. So the load cables, the neutral cable goes directly to the panel board. If there's a fault, the current path to clear the fault, assuming we're properly bonded, the current fault clearance goes back through the grounding conductor, and we open it up there, and so we don't have fault currents in neutral conductors, which will upset equipment, possibly damage equipment. So I think that's the great thing about having an isolation transformer in the inverter, and then a local bypass isolation transformer.
No, absolutely. And, you know, I've never seen it, but one of the other reasons why we have the isolation transformers is to stop the DC inside the UPS from propagating either back onto the MCC that feeds the UPS, or if there's a failure in the inverter bridge circuitry in a system that doesn't have a transformer, then that DC could propagate onto your load circuits as well, which can cause damage and misoperation of the load circuits. With a transformer, with an isolation transformer there, DC can't get through a transformer. So if there is a fault, then the isolation from the transformers prevents the DC propagating onto either AC supplies. Okay, I think that is about all the questions that we have. What I would like to say, as always, is thank you very much for taking the time out of your day and watching and listening to this webinar. You will be sent a survey after the webinar asking which topics you would like to be discussed at our next webinar. We would really like the input from our clients to know what you would like us to discuss and talk about. So please fill out that survey if at all possible and let us know. I'm just looking at, just waiting to see if there's any more questions coming in. Somebody's asking if we send a presentation. Like I said, we're going to put the video from the presentation up on our YouTube channel, and you can rewatch the presentation at your leisure. Everybody who has signed up will be able to view it on YouTube. You'll be sent the link. So that's been an hour and 17 minutes. We overrun, which we tend to do because we love talking about the stuff that we make and all the ins and outs. I'd like to say thank you very much to Don. As with my very first webinar, there's always things that catch you in the background, and that's just the way it is. And it usually puts a smile on our faces. It lets us know that we're live and we are just being human, I suppose. So once again, thank you very much. I appreciate everybody's attention, and we will send another invite out next month for our next webinar, and hopefully you have the time to take out of your day and watch it. Anything you'd like to say, Don, before we go? I'm just thankful everybody stuck with me for this. Transformers are not always the most enlightening experience, so I appreciate everybody that stuck with it here. Okay, and that's just about perfect timing because I am at home, and it seems like the lawn crew from next door are just starting to kick up with the leaf blowers and everything. I don't know if you can hear it in the background, so it's a good time to say goodbye. So thanks again, and we will speak to you again next month.